Hey everyone, and welcome to our last lesson in our course of study on Regents chemistry. Today's lesson is going to be on organic reactions. And what you're going to be able to do by the end of this lesson is to identify a few different types of organic reactions. And really, this is a pretty complex topic, and there's a lot in here. But we are just going to scratch the surface of this topic. And really, this is just kind of a few different types of reactions that the Board of Regents would like you to be aware of and how they can contribute to making complex molecules. So, as I said, there's a lot of different types of organic reactions. We're going to talk about 6 general types today. You're going to need to memorize a few of these, and using a little common sense for many of these is going to go a long way. This can generally be a pretty tough topic, but we're only going to scratch the surface of this, so this shouldn't be too bad. I mentioned in the previous lesson about dehydration synthesis. You would have learned this in biology. This is responsible for several different processes with DNA and within the cell itself. And if you break apart the name of dehydration synthesis, it's relatively easy to figure out what it is. So dehydration means to remove water, and synthesis means to link or put together. So this type of organic reaction involves linking or combining 2 different organic compounds by removing water from the functional group. For example, esterification undergoes the organic reaction dehydration synthesis in order to make an ether. And in order to make an ether, we need 2 alcohols. They can be the same, they could be different. This reaction does require a dehydrating agent to help remove a hydrogen and hydroxide from each of the functional groups to make the water molecule. And sulfuric acid is going to be the choice for this particular reaction. And we see that written right above our reaction arrow here. And that's just telling us that the sulfuric acid is helping to combine, in this case, the methanol and ethanol, but it's not being used up in the reaction itself. We don't see any of the components of the H2SO4 involved as either a reactant or product as far as our conservation of matter. And in general, when we see that above the arrow, these items, oftentimes catalysts, are not consumed in the reaction. So in this example of dehydration synthesis, we're going to start with 2 alcohols. We'll use sulfuric acid as that dehydrating agent, and we're going to end up with 2 different products, the water molecule and our ether, in this case methyl ethyl ether, resulting from the combination of methanol and ethanol. And these are lined up just right, so we can see how the sulfuric acid helps to remove this water molecule by removing a hydroxide ion and a hydrogen. And that's going to combine to make our water. What's remaining here, we have our ether functional group, the oxygen in between 2 different sets of bonded atoms, 2 different radicals, and we get methyl ethyl ether. And this only occurs because we remove the hydroxide and the hydrogen from each of the functional groups on the methanol and the ethanol. Now, esterification is pretty similar. This is going to create an ester as opposed to an ether. And this requires an alcohol and an organic acid. And remember, esterification or esters are responsible for smells and flavors in several different kinds of foods. And it's named for the alcohol and the acid that formed it. Alcohol name will become first, followed by the organic acid name. And we're going to use sulfuric acid again as a dehydrating agent in order to help remove water from the functional groups of both reactants. So in this case, we start with ethanoic acid. being our organic acid, and 1-butanol being the alcohol. And we're going to use sulfuric acid again to dehydrate a water out of these two functional groups of these two molecules. And then this oxygen simply bonds over here with the carbon. And we're left with the ester functional group, the C with the double bond O and another single bonded oxygen. We see that the name of the alcohol becomes butyl, and ethanoic acid gets converted to ethanoate. So we're naming this butyl group derived from the alcohol here, and that's becoming the first part of our name there. So it is a hydrocarbon chain that is attached to that ethanoate. Next reaction is fermentation. Most of you should be pretty familiar with this, having taken biology. Fermentation is the breaking down or conversion of glucose or fructose, some type of sugar, in fruits and vegetables. And this reaction, which is catalyzed by zymase, converts sugar into a form of alcohol and another product, carbon dioxide. This is a pretty common reaction that we find in nature. Saponification. Saponification, as it sounds, is the making of soap. It requires a glycerol ester, which is a fat, and sodium hydroxide. And the base is going to work to help remove this hydrocarbon chain off of the end of the glycerol stearate. And it's going to create two different products. The sodium stearate, which is our soap, and glycerol, another byproduct. And this sodium stearate, which is written in its condensed version here, comes from the glycerol stearate, which had the end removed by the sodium hydroxide, and the sodium attaches to the end of this molecule. And what that does is makes this end a positive dipole. The end over here is nonpolar. And this is the reason why soap can dissolve fat and water together. The nonpolar end of this molecule, the long 17 carbon chain, is nonpolar and therefore allows nonpolar solutes to dissolve into it like fat or grease. And then this positive dipole arising on the other far end of the molecule is polar, so it can be attracted to a water molecule, which would also have a charged end. This is going to allow soap or allow water and fats to mix with each other. Polymerization, another reaction that you've probably heard of before, but maybe aren't quite as familiar with what exactly it is. But polymerization is where we take a polymer, which is an extremely large molecule, that's made by connecting smaller, what we call monomer, you might remember this from biology, smaller monomer units together. And the basic molecules are the building blocks of the polymer. So if we attach two monomers or more together, we get a polymer. And these molecules can take on an enormous size. And the reaction of how they look is a little bit different. And really what this is saying is that we have a monomer molecule called A, and we're going to start with 18 of those. And through the reaction of polymerization, we're going to end up with 18 A monomers bonded end to end to each other. And we see that shortened version here. given reactants we start with, and then we see this kind of open-ended chain here on either end of the A, which is going to show that we can connect more monomers together. And that'll continue on 18 times. Now there's a few different types of polymerization. Addition polymers are formed when the monomer's double bond opens up and the monomer units kind of just join end to end onto each other. And to name these types, all we do is put poly in front of the monomer name. So if the monomer is vinyl chloride, we put poly in front of the name and we get polyvinyl chloride, which is PVC. That's that, the white pipe that you see oftentimes for plumbing is PVC pipe. And it's in a lot of other things as well. Polystyrene, we can pick out the monomer, styrene, and if we put a bunch of styrene end to end together, add them all together, we get polystyrene, which is known as styrofoam. Polytetrafluoroethane, if we kind of break that down, we take out the poly, our monomer unit would be tetrafluoroethane. When we put a bunch of those together end to end, and in addition, polymer reaction, we get polytetrafluoroethane, or Teflon. Condensation polymers are formed from monomer units that have an alcohol functional group on one end and our carboxylic, which is our organic acid functional group, which is the COOH, on the other end of the molecule. The opposing ends will undergo dehydration synthesis, remove a water, and they will form the polymer. In this case, the monomer being the ester. Rubber, another example, is formed from addition polymerization, and another product that is made from oil. And this reaction to produce rubber will link these different monomer units in the rubber with sulfur in a process that we call vulcanization. And this interlinking between rubber monomers and sulfur helps make the material much stronger. And I kind of threw a lot at you there, and we're just going to kind of review a little bit of these and what you really need to know. And you need to know how to recognize a reaction when you see it. And this can be done by looking at reactants or products, sometimes looking to see what catalyst is being used to indicate what reaction it might be. And then you'll also be able to, or should be able to, determine the reactants needed to make a particular product. And that is a little bit harder to do. So looking at these, we'll do a few examples here. I'll try and run through these pretty quick. We have CH4 and O2 that form CO2 and H2O. We talked about this one prior, and the best way to recognize this is seeing that we have a hydrocarbon that's reacting with oxygen. And every time we see that, if we see that these two products are formed CO2 and water, we want to think combustion. This would be the reaction that's occurring at your lab bench in your burners. So the products that we're getting off of those Bunsen burners are CO2, water, and heat and light. Now why? Well, we have an organic compound reacted with oxygen, forming those two particular products, CO2 and water. And that's an indication of combustion every time. With this one, we have a hydrocarbon reacting with a halogen, and we see that our number of hydrogens is going to decrease, and now we have a chlorine added onto here. And since we have a decrease in the number of hydrogens, in this case this is a alkane, another indicator, 2N plus 2. This is going to be substitution. So we have the chlorine substituting with a hydrogen on the alkane. And I highlighted this as an alkane because we don't have a double or triple bond, which would lead us to a different type of organic reaction that we learned prior. So the key here is that we have the number of hydrogens decreasing and a chlorine's taking the place of that hydrogen in the hydrocarbon. For each of these, feel free to pause them, try and determine what type of reaction it is, what the indicator is, or what reactants or products you might need. In this case, we have glucose, C6H12O6, reacting to form CO2, and this has the alcohol functional group. So this is CO2 and alcohol, which is fermentation. And we don't see the catalyst written here, but oftentimes this reaction does use a catalyst, although it doesn't need a catalyst. Now going back to one of our previous examples, it's important to try and determine the general formula for a hydrocarbon. In this case, this would be an alkene. It fits the 2N formula. I should say CN H2N. So we have twice as many hydrogens as we do carbons, which is going to indicate an alkene, which is going to have a double bond in that molecule. The halogen, nothing changes here with our hydrocarbon, and the halogen simply gets added onto the molecule. And I point out that it's an alkene because we have a double bond, and that double bond is going to break. Chlorine is going to add onto the molecule, and this is an addition reaction. So we have no hydrogen atoms that are removed. The chlorine simply add on to the propene molecule, break that double bond, and add onto it. So we have an organic acid and an alcohol. And we see that we have water that's being removed at the end. And there's two reactions that we looked at with removing water. And depending on the types, it'll help us determine what the reaction is and what we're going to produce. So this is esterification, combining an alcohol and an acid. And we recognize that C double bond O in the middle of the molecule. We have the alcohol, two different alcohol functional groups and two different molecules. Again, we're seeing water that's being removed during this process. This is another dehydration synthesis reaction. And each of these are alcohols, indicated by their functional groups. When we combine two alcohols, this is esterification. And we can see the ether functional group in the middle of that molecule. I always think that these ones are kind of stick out like a sore thumb. We generally see really large numbers with these types of reactions. And we're given one reactant, almost kind of like fermentation. But a dead giveaway are these open-ended brackets. And the product followed by the large number that came from the beginning. So this is polymerization. We're going to add C2H4 monomers together, 5,000 of them. So we always are listed the monomer with how many monomers are going to be added together during the polymerization reaction. Now for these, we're going to want to try and figure out what our reactants we're going to need in order to produce this product. So if we wanted to make ethanol, an organic reaction that produces ethanol is fermentation. So in order to make alcohol with fermentation, we're going to need a sugar, glucose or fructose, and yeast. Something that's going to be able to ferment that sugar into the alcohol. Now, our desired product is 1,5-difluoropentane. And we have two spots here on the first and fifth carbon. So we have pentane, right? So pent would be our 5-carbon alkane with the ending here, ane. And we have two fluorines, one on the first and one on the fifth of that pentane molecule. How do we get halogens onto a hydrocarbon? Well, we're going to have to use substitution. So we're going to remove hydrogens off of the ends of the molecule, not in the middle, but on the ends. That's why we have 1,5. We wouldn't see them in the middle. They're only going to be on the ends. In order to do this, we're going to need fluorine, which is diatomic, and we're going to need pentane. And we'll simply remove hydrogens off of our pentane and add on 2 atoms of fluorine. The desired product, 2,3-difluoropentane. This looks pretty similar, but the key here for this one is the numbers of where the fluorines are. And since they're not on the ends, this is going to indicate that we're going to need an addition reaction. So substitution is going to show numbers with our halogens on the end. And if we have halogens in the middle of the molecule, we're going to need an addition reaction. And the reason why they're in the middle of the molecule is because we had a 5-carbon parent chain, but in order to add fluorines on the second and third carbon, we're going to need a double or triple bond in that molecule. And in this case, we're going to need a double bond. So we're going to need 2-pentene, double bond on the second carbon, and diatomic fluorine. And this bond will open up, and we'll be left with 2 bonding sites in order to add the 2 fluorines onto that molecule. For this one, the desired product is ethyl propanoate. And what I would encourage you to use is your reference table R to look at some of these names and try and help you figure out, okay, well, here's an example name. It looks similar, so it must be, in this case, it's going to be an ester because the name here matches to our example name on table R. So the product is an ester because of that ending, propanoate. And in order to make this, we're going to need an organic acid and an alcohol. So we're going to need ethanol. Remember, this first part here of our name is the alcohol, and the second part is derived from the acid. So ethyl would come from ethanol, and propanoic acid would become propanoate. Desired product, methyl propyl ether. The ending of this one helps indicate what reaction we need, and this would be etherification. That's going to make our ether. And these are going to require 2 alcohols. We have a methyl and a propyl. And these are just going to be simple alcohols, methanol and propanol. And we'll remove a water when we combine the 2 of those together. For this one, if we want to make polyisoprene, well, it has the poly designation in the beginning, so therefore it should indicate that it's polymerization because of that prefix, and the monomer is always followed after that. So the reactants that we need is isoprene, lots and lots of isoprene. So this is the basis of organic reactions that we're going to touch base on this year. And if you happen to take this course, organic chemistry, in college, you'll dive a lot deeper into the various other types of reactions or even then, still just kind of scratching the surface with what's involved with organic reactions. If you guys have any questions, make sure you write them down and come see me to get them answered. Hope you guys have a wonderful day and great job.